In this video, we will learn about how alkenes can undergo oxidation and reduction reactions. We'll start off with oxidation reactions. When we're oxidizing alkenes, what we're thinking of doing is that we're actually going to break the carbon-carbon pi bond and create two new carbon to heteroatom sigma bonds. A first example of such an oxidation reaction is a common one known as epoxidation. If you've heard of epoxy glues, that comes from the epoxidation of alkenes. Epoxidation uses a peroxy acid to yield a functional group called an epoxide through a concerted and cyclic mechanism. So an example of such a reaction would look like this, where I have just a 2-methylbutene here reacting with this molecule, which is a peroxy acid. You'll notice it looks like a carboxylic acid, but has an extra oxygen between the O and the H. This oxygen-oxygen single bond is what gives it the peroxy prefix in the name. This particular reagent is very common and is known as MCPBA, standing for metachloroperoxybenzoic acid. After the reaction, what you get is a 3-membered ring with an oxygen in it. This is the epoxide functional group. And what you see is that you have the 2 carbons of the alkene having formed single bonds to oxygen. Epoxides are somewhat strained, but they are not as strained as cyclopropanes because the lone pairs on oxygen here take up a little bit more room according to Vesper theory. That overall makes it so that there's less angle strain in an epoxide compared to cyclopropane. Let's look at the mechanism for this reaction. So this is concerted and cyclic, so it's actually pretty quick and simple. What you end up trying to do is you set up the drawings this way. And what we're doing is to take advantage of this terminal oxygen here as being the electrophilic part of the molecule. We're viewing the carboxylate up here as a potential leaving group in the reaction. So you can think of this almost like a halogenation reaction where we attacked bromine and broke the bromine-bromine bond. Here we're attacking oxygen, breaking oxygen-oxygen bond. So we'll start off with that. Take our pair of electrons in the pi bond, attack the oxygen. We'll break the oxygen-oxygen bond. We'll do it such that it just undergoes kind of what looks like the resonance process, but in doing so allows us to go ahead and just simultaneously deprotonate this hydrogen from the end of the peroxy acid. This is okay to do because we have a 1, 2, 3, 4, 5-membered ring in our transition state here, so it's not too far to reach. Once that happens, then we have a oxygen-hydrogen pair of sigma electrons that need somewhere to go, and that pair of electrons is doing the biting back to form the 3-membered ring. So overall, again, that gets us to our epoxide and a benzoic acid as our leaving group, more specifically the metachlorobenzoic acid as our leaving group. Epoxides are very useful as a functional group, which will be learned about in future videos, but they are really good electrophiles because they do have some amount of strain, and so attacking these and breaking open the ring can relieve a lot of strain, making it a very reasonable reaction. So an example of that would look like this, where a cyanide nucleophile is attacking the epoxide and breaking it open. A second type of oxidation reaction is called a dihydroxylation, where we're putting 2 hydroxy groups onto the alkene carbon, so 1 per alkene carbon. This is done using tetroxide reagents, so reagents with 4 oxide pieces on them, and this follows, again, a concerted and cyclic mechanism. So a common kind of set of reactions will look like this. So a tetroxide reagent is referring to things that look like this here, where there's 4 oxygens on a metal, so tetraoxide. And during this reaction, you go through an intermediate that looks like this species here, where we formed what is going to be called a metal ester. When it's osmium, then this is an osmate ester. When it's manganese, then it's a manganate ester. This ester can then be hydrolyzed, much like a carbonyl substitution, to get to the diol product. So the mechanism for the initial creation of the osmate ester, for example, looks like this. Well, what we're going to imagine is the alkene pair of electrons actually attacking oxygen now. This will feel a little funny and different, but this pair of electrons between osmium and oxygen will go back to the osmium and then lead to kind of what seems to be like pushing this pair of electrons to the oxygen, but really we can just use that to bite all the way back to here, creating a carbon-oxygen bond over on this side. This gets us to the osmate ester. This osmate ester, then depending on the specifics of the reaction conditions, can then be hydrolyzed. So if there's water around, they can be easily hydrolyzed through kind of typical substitution type of chemistry to get to the diol. You'll see that this reaction has to be stereospecific because it is happening all simultaneously. So these two atoms have to add to the same side of the alkene. It's impossible physically for one of those oxygens to be above and one oxygen to be below. So again, a stereospecific syn addition. It turns out that osmium is highly toxic, and so if you're looking at this reaction up here, for each alkene I want to dihydroxylate, I need to use 1 molecule of osmium tetroxide. That's considered to be inefficient in terms of what's called atom economy, so we're not being very kind of economic because we're using 1 toxic atom per reaction that we're conducting. A solution that people have come up with is to make it so that the reaction is instead catalytic in terms of osmium. And so the version of this that has been developed is called the Upjohn dihydroxylation. An example looks like this here. So instead of using 1 molar equivalent, or we could consider that 100 mole percent of osmium tetroxide as we did up here, now we're using just 5 mole percent osmium tetroxide. So I guess 5% as toxic. The key is to use an additive here. So this is NMO. NMO refers to N-methyl morpholine oxide, which is the morpholine is referring to this 6-membered ring. The N-methyl is the methyl group here, and the oxide refers to this type of a functional group, where an N-oxide is when you have a negatively charged oxygen single bonded to a nitrogen atom. We're not going to go through the mechanism for how exactly this process becomes catalytic. The idea is that if you look at what's going on up in the initial reaction, the osmium is going from having 8 total bonds to oxygen. So this is an osmium with oxidation state of 8. And after the reaction, it now turns into an osmium with an oxidation state of just 6. And so our active oxidant needs to have oxidation state 8. And what NMO does is that through all sorts of processes, it turns osmium 6 back into osmium 8. And so that regenerates the oxidant, allowing it to react again. This will be considered much more atom economic in terms of osmium, at least, because we only need 1/20th as much osmium to conduct the exact same reaction. A third type of oxidation of alkene reaction is ozonolysis. This one is very interesting because it's going on in the atmosphere all the time in the ozone layer. It's a very versatile reaction on Earth as well, and it actually takes alkenes and cuts them in half. So we cleave them into all sorts of different functional groups, and the identity of what you get depends on how you do the workup of the reaction. An example of such an ozonolysis looks like this, where I am taking this alkene. I'm showing you the ozone, so O3 as the reactant, and in the second step I'm doing a dimethyl sulfide workup. Turns out in the end this makes an aldehyde from the left half and a ketone from the right half. So what you're seeing is that essentially we've cleaved that carbon-carbon double bond in half, and we've created some carbon-oxygen bonds on both sides from where we cut. Right? So here we've gained some bonds to oxygen. On the right side we've also gained bonds to oxygen. That's a little hard to see. Sometimes it's helpful to visualize it as such, where I'm starting with that molecule and just breaking it in half like so. The mechanism for this reaction is the source of all sorts of interesting research, but the first part involves what's called an ozonide formation. And so what we start off with is a reaction that looks like this here, where ozone has kind of a dipolar nature to it because it has this charge separated state in there. And so we have a nucleophilic oxygen and an electrophilic oxygen. But if you think about carbonyls, where when we had positively charged carbonyl oxygens, it was actually the other atom that was electrophilic. Same thing here. We have an electrophilic oxygen at the end, nucleophilic oxygen at the other end. So then overall, what we're getting is a reaction that looks like this. Kind of our initial nucleophilic attack of the alkene onto this oxygen-oxygen double bond. Then we have the nearby nucleophilic oxygen that's able to bite back. This is called a cycloaddition reaction because we make a cycle after the reaction. So then you get to this crazy looking compound with 3 oxygens bonded together. This is a primary ozonide. This is a usually very unstable species, often explosive, and so ozonolysis reactions have to be done with a lot of care. This primary ozonide is so unstable that usually in a reaction it just decomposes right away spontaneously on its own, and it will turn into actually 2 separate molecules, and this is going to happen like so. It kind of should remind you of a carbonyl tetrahedral intermediate collapse. Either way, we're kind of forming overall the 2 what look like carbonyls. So I'll start off with a lone pair from just the left side here. That's collapsing. That's breaking the carbon-carbon sigma bond. That then creates a new carbon-oxygen double bond on the other side. And the leaving group is actually this oxygen up here. So you see an elimination taking place here, and then an oxygen breaking to get you to, again, a negatively charged oxygen, positively charged oxygen. One thing I want to point out here is that I wrote this going clockwise. You could also do the same process going counterclockwise, and you would end up with a different pair of what's called carbonyl and carbonyl oxide here. So either way is possible, and either way will happen. You can imagine that this combination is also not very stable, and what then happens is that this recombines very quickly to form a new species, and what it does there is that the negatively charged oxygen is actually nucleophilic and attacks the neutral carbonyl. That then pushes a pair of electrons up, but will do it in a way such that it just ends up attacking the other carbonyl, which is definitely electrophilic because it has the positive charge on there. And then that then pushes another pair of electrons onto that positively charged oxygen, getting us back to something neutral. That's going to look like this species right here. This is a secondary ozonide, and it's a little bit better because we just have one oxygen-oxygen bond, which is usually the source of instability, and has kind of separated out and made an ether on the other side. If you have a hard time seeing exactly how this is happening, I have it drawn in a slightly more organized form. So what I did is I just took this ketone, redrew it, and flipped it, such that this now looks more kind of like a cycloaddition, the same way that you saw initially here. And so this is what's happening in real life, right? So you fragment the primary ozonide into 2 pieces. These are already next to each other, so they're much more likely to collide. And when they collide in the way that looks like this now, if this molecule kind of did a rotation and then collided, you make a secondary ozonide. Secondary ozonides are much more stable, and it's possible to isolate these sometimes, but these can still be explosive and very dangerous. So usually then, when running an ozonolysis reaction, the idea is to run the reaction until you're sure all the alkene has been reacted away, and at that point, just go ahead and perform the workup right in that flask and not try to isolate any of this ozonide. There are 3 common ways to do this workup, each resulting in a different set of products. You can do what's called an oxidative workup, in which you are cutting all of this apart and oxidizing everything up as much as possible, getting you thus to either carboxylic acid or ketone. So what we're trying to visualize here is that the 2 carbons where the alkene had been before, those are ending up as oxidized as possible. A second option then is to do a reductive workup, where usually people are using either dimethyl sulfide or triphenylphosphine as the source of reduction. And here the reductive aspect of it is actually the source of electrons rather than a source of hydrogen. But that's a little bit of a technicality we're not looking into in terms of a mechanism. What you get at the end of the day is the carbons of the alkene in their second oxidation level. So in other words, what we're doing is just not oxidizing all the way up to carboxylic acid. We're keeping things at either aldehyde or ketone. Finally, if you want to do a more aggressive reductive workup, you can, instead of ending up with carbonyls, end up with alcohols. And that works just by using a stronger reductant, or sodium borohydride, which already should be known to be able to reduce aldehydes and ketones into their alcohols. Now, let's look at reduction of alkenes. In carbonyl reduction, we think about adding H2 across the carbon-oxygen double bond. In carbon-carbon double bond reduction, we do the same thing. We are adding H2 across that double bond. The way this is done most commonly is to perform the hydrogenation reaction with a heterogeneous metal catalyst. The word heterogeneous means that it's not a dissolved metal catalyst. So in normal organic reactions, we are considering all of our reactants to be totally dissolved and solvated. But when we're dealing with heterogeneous reactions, then some stuff will not be dissolved. In this case, the catalyst is not dissolved. And so it's just a solid that is kind of floating around in the reaction flask. A common reaction will look like this, where we take our alkene, we're reacting with hydrogen gas, and commonly a palladium on carbon reagent is used. This is the catalyst, and the structure of this is, well, it's not a dissolved single atom or a dissolved single molecule. It's a bulk material, so we're supposed to imagine that palladium on carbon is just a bunch of these palladium and carbon atoms like a metal, just all kind of together in kind of a large aggregate here. So I'm drawing it as a single sheet, but you can find these in all sorts of shapes, like kind of more kind of 3D polygons or other shapes like those. Whatever the case is, what we have is just a large surface of extended palladium and carbon atoms. So because of that, it becomes very hard to study the mechanism for this reaction. All the spectroscopic techniques that you've learned about in the past are on single molecules dissolved in solution. And so what we have here is, again, a potential mechanism, not necessarily the most accurate representation of reality. So what we'll do is to think of the catalyst like this, like just a solid mass, and we'll think of it reacting with a molecule of hydrogen. And what we'll think of this doing is that a pair of electrons from that hydrogen single bond will come down and kind of attack the catalyst, and at the same time, somehow the catalyst will attack back. This will get us to a state that looks like this, where there are two hydrogens bonded to the catalyst. And of course, we're taking this in isolation, but in reality, because this is such a large extended amount of palladium atoms, you should have lots of different hydrogen atoms bonded to the catalyst, but for our mechanism, we'll just look at these two. An important thing to realize here is that two of these electrons came from the hydrogen gas, the other two electrons came from the catalyst itself. Then, this alkene will kind of be floating around and eventually collide with the catalyst and kind of associate with it and just like kind of stick to it through an intermolecular interaction. This is because metals are usually a little bit Lewis acidic, which means they are needing a little bit of electron density, and alkenes are providing that electron density. As that happens, then these nearby hydrogens, which if you remember have some hydride character to them because what we thought of was this H- coming down into the catalyst. So what we'll think about is this as an H- potentially being reactive and the other one as an H+. Then our reaction will look like this. Since we're thinking about alkenes, we'll always use them as a nucleophile first. We'll have that attack the catalyst to form a catalyst to carbon bond. And then at the same time, our H- will come back in and kind of fill that void that is left when a pi bond acts as a nucleophile. This gets us to something like this, where now our reactant is actually bonded to the catalyst, and we've created a new carbon-hydrogen bond. The next thing that then happens is that the other hydrogen, I think of this as essentially just kind of sliding in and taking the place of the catalyst to carbon bond. This then frees an alkane to float away, and the catalyst is regenerated to be able to continue reacting. This reaction is not exclusive to alkenes, so alkynes can also get reduced, and they will get reduced all the way into alkanes. It turns out it's very impractical to run this reaction and just say I'm going to stop halfway, because alkynes and alkenes are about similarly reactive to hydrogenation, and so then most of the time what you see is people will take their alkynes and go straight to an alkane. You can imagine, however, that there is value in being able to turn an alkyne into an alkene and stop there, especially because we've been talking about electrophilic addition reactions to alkenes. There's definitely a lot of other paths you could go once you have an alkene. And so the way that we do this is to reduce the catalytic ability of the catalyst by using a bit of what's called poisoning. There's a lot of different ways to achieve this poisoning, but at the end of the day, what is always happening is something is being added to the palladium catalyst, or in this case up here, platinum catalyst, and that is causing that catalyst to be less effective. So an example of this is here, where the barium sulfate is the additive that is poisoning the catalyst here. So this is a poisoned catalyst. And what you'll see is that then this alkyne will get reduced, but you only get the addition of 2 hydrogens, and that stops right there. Notice that because of the mechanism of the reaction up here, the addition is happening syn, so the 2 hydrogens of H2 gas are adding to the same side of the alkyne, thus resulting in a Z alkene. So again, this is a syn and stereospecific reaction. Naturally, you'll wonder, well, can we achieve that same type of reduction but get to the other alkene isomer, so the E alkene? Turns out the answer is yes, but we have to do it in a very different way. And the way it's done is to use what's called a dissolving metal reduction. And this goes through a new type of mechanism called a free radical mechanism. So I'll just show you first that if you take the same alkyne, so this is the 3-hexyne, and use a dissolving metal reaction condition, then you can get to this trans 3-hexene. When we're dealing with free radicals, we need to have something generate a free electron, and so that's what this sodium is doing. Sodium solid, or sodium metal, is a very, very strong reductant. In other words, it's a very, very strong source of a free electron. And so when we're thinking about dissolving metal reduction reactions, what we're really thinking about is that the reaction conditions create a free electron, just floating on, just an electron as a reactant. So the mechanism looks like this. The sodium we can think of as just sodium with 1 electron on it. The technicality would be that maybe this electron is totally separated and free, or we could draw it this way. Either way is really going to be fine. But what we're going to show is that this sodium is going to reduce the alkyne by adding this electron to the alkyne. The way I'm going to show that is to use a single-headed arrow because a single electron is being transferred. And I'm going to use, again, a single-headed arrow to kind of break apart my alkyne pi bond here. And so again, the blue arrow here is indicating an electron transfer from one species to another, not a bond formation. After this process, what we get looks like so, where I've paired the sodium's electron with one of the electrons in this pi bond, and I've left an unpaired electron on the other carbon atom. So I get a free radical and a carbanion, in addition to the sodium cation. This is not that stable, so of course this is only possible because sodium itself is so reactive and such an unstable source of electrons. And so the key here is that this species is able to equilibrate and go between the 2 kind of isomers, so we can kind of think of this lone pair as inverting to the other side to get from the what looks like the Z alkene to the E alkene. This is sterically a little bit better to get the 2 large groups away from each other, and so this dominates in the equilibrium. And as this equilibrium happens, then occasionally these will collide with a molecule of ammonia. If you look at pKa's, it makes sense that this is a stronger base than NH2-, and so an acid-base reaction happens, getting us to the protonated alkene with a free radical still on it, and now this amide conjugate base. This then gets reduced again by an atom of sodium, so another free electron generated from sodium is just added directly to this free radical here in a way that essentially we can think of it as now creating a lone pair, right? So now we've created sodium cation and now an alkene carbanion. Can go through the same acid-base process then to get to the final desired alkene product. So in this video, we saw a few different ways to take alkenes and transform them into other functional groups. So first we looked at some oxidations, so to turn these alkenes into carbon-oxygen single bond and carbon-oxygen double bond containing molecules. And then we looked at some reduction reactions where we're able to transform alkenes and alkynes down into either alkenes or alkanes.